So let's take a look. So what do we learn in that example? So ionization energy is the external energy that needs to be given to an atom to remove an electron. All right? And so the energy required to remove the first electron from the valence shell is called the first ionization energy. But there are second, third, fourth, fifth, sixth, seventh, as many ionization energies as there are electrons to be taken. All right? What do we learn about how much energy it takes? It depends on how tightly that electron is being held by and who's holding the electron? The nucleus. All right? And you want to remember that for this, magnetic attraction is dictated by distance. Let's just look across a period. So again, let's look at the same three elements again across the period: lithium, nitrogen, and neon. Remember back when we talked about how this had 3 protons, this had 7 protons, this had 10 protons? And so because this has more protons, it's being pulled in more closely. So the radius is smaller, and we depicted that as a big fat arrow. And then over here, the strength isn't quite so much, so we drew a skinny arrow. And here in the middle, it was kind of an intermediate arrow. All right, so which one of those is being held more tightly? Neon. So where am I going to have to spend the most energy to rip it out? In neon, right? Okay, as a matter of fact, if I give you the quantity for that, the ionization for neon is 2081, and the unit for ionization energy is something called a kilojoule per mole. Don't worry too much about that, just worry about the number. All right, nitrogen, the ionization energy for that is 1402 kilojoules per mole. And then for lithium, it's 520 kilojoules per mole. I don't need you to memorize those numbers, but doesn't that make sense? The number gets bigger. Why? Because that electron's closer to the nucleus. So if someone wanted to come from the outside to snatch that electron away, they're going to have to spend that much more energy. So if the electron is closer to the nucleus, it will be held more tightly. This will require more energy to be added to remove it. All right? Now, let's take a look at this column. Yes? Those are the number of protons in those atoms. Because protons are positively charged. Okay? All right, let's take a look down the family. All right, do I look at protons down the family? What do I look at instead? Shells. All right, so here, this is being pulled, but what are those other layers in between doing? They're pushing. As a matter of fact, you've got 2 layers that are pushing outward. You have 1 layer that is pushing out in the case of lithium, 2 that are pushing out in the case of sodium. How about in the case of potassium? You've got the nucleus pulling in, right? The protons in the nucleus pulling in. But here, there are 3 layers of core electrons pushing outward. All right? What do these forces do to that electron? Do they push it away? Do they make that electron, does it make it get further from the nucleus? Does it make it easier to come and steal that electron if you're further away? The answer is yes. All right, so here again, if it's closer to the nucleus, it's going to be held more tightly. It's going to require more energy. All right, so lithium, the ionization energy value is 520. For sodium, it's 496 kilojoules per mole. So it takes less energy to steal that electron than that one because it's further away. And then over here, it's going to be 404 kilojoules per mole. Again, because this is even further away now by putting all these extra layers in the middle, it's going to take less energy to steal that guy away. All right? Now, one of the things that I do want you to be mindful of is that these pictures are kind of messed up a little. All right? I only drew 1 electron in them on purpose because I only wanted you to focus on this concept of first ionization energy. But in reality, nitrogen doesn't just have 1 electron in its outermost layer. It actually has 5, right? So you can draw them in if you want. Okay? And neon really has 10, so you can draw those other 9 in if you want. But I only really want you to focus on the big one that's that's on the ring. Okay? Yeah, draw them in. All right. Now, where are the largest ionization energies on the periodic table? Who has the largest value? Neon. Well, according to this picture here, right? But really, like what corner of the periodic table is that? All right, so who's the biggest value, left or right? Top or bottom? So top right is going to have the highest ionization energy. So what element do you think is going to have the highest of all of them? Who's on the top right? Helium. All right? And then the smallest. All right, so where are we smaller, on the left or on the right? On the left, on the top, or on the bottom? Bottom. So bottom left is going to have the smallest ionization energies. Who's on the bottom left? Francium. All right? Now, if you look at the front page, how does this pattern match what's on the front page? It's the opposite. Okay? So this is the opposite as radius. Okay? So this trend is the opposite. All right. Let me show you another thing. Right. This pattern is the complete opposite of radius. Okay? All right. We talked about having second, third, fourth, fifth, and sixth ionization energies too, right? So that's the energy needed to take subsequent electrons away. So let's take a look at the example here, lithium. Which one of those electrons would go first? The gray or the black? The black. So this one would go first. And then what would go? One of the gray ones. It doesn't matter which one you take. All right? The energy needed to remove the second electron in this specific example, is it going to be greater than, less than, or equal than removing the first one? What, Jasmine? It's greater. Why? Because the second electron is held tighter by the nucleus, because it is closer to the nucleus. The energy required to remove the third electron will be equal to the second, because they are the same distance from the nucleus. All right, we're going to finish the next sentence, and then I'm going to show you a quick little video, and then we'll come back and finish this off. Ionization energy of metals, and metals, specifically metals, so I'm going to highlight that, helps one to predict their reactivity. All right? Reactivity. And this is because metals prefer to lose electrons. So the reason why metals conduct electricity is because they are just shedding their electrons. And electricity is just electrons running in a wire. All right? I'm going to, let me just finish filling this out, just so you have the answers. Okay, so the smaller the ionization energy, the more reactive the metal. For example, the most reactive metal in the alkaline metal family is francium, because it doesn't take much energy from the environment to get it to lose its valence electrons. Likewise, alkali metals have larger reactivities in alkaline earths because they only have to lose one electron instead of two. Just write those answers down. Just write them down. I'll explain them, but I have to show you a little video first. Okay? Yeah? I should, because I talked too fast? Oh, that happens. All right, I just need you to copy what's on the board.